Welcome to Deep Dive with Phil and Emily. Today we're diving into the world of mathematical norms with you.
Oh, cool.
And I gotta admit, before prepping for this, I thought norms were just about finding the length of a line.
Okay.
But there's so much more interesting than that.
Yeah, they are.
So we're going to be drawing from a lecture by Professor Wu.
Right.
He's a real expert in this area.
He is really great. Yeah.
He helped me to see norms as like these powerful tools for understanding size and distance.
Yeah.
In like really unexpected ways.
Yeah. Okay, so let's unpack this a little bit.
Right.
We often use mathematical functions to pull out specific pieces of information from a set of numbers, right?
Yeah.
Like if we have a bunch of numbers, we might use the max function to find the biggest one.
Yeah, exactly. Think of like max, min, or average.
Right.
They all take a set of numbers and then tell us something specific about them.
Oh, okay. So is a norm basically just another one of those functions?
It is.
Okay. But instead of finding the average or the biggest number, a norm tells us about the size or length of a vector. And this is where it gets interesting because we're not just talking about length in the typical one-dimensional way.
Okay, so you're saying that the idea of length can exist in multiple dimensions.
Absolutely. Remember, absolute value.
Yeah.
The thing that tells you how far a number is from zero on a number line.
Yeah, I remember that.
Well, absolute value is actually a type of norm. It's the norm for one-dimensional vectors or just numbers, but when we move beyond a single dimension, things get more complex.
Okay, so how do we measure length when we're dealing with multiple dimensions?
That's where different types of norms come in.
Okay.
It all boils down to the fact that distance isn't always a straight line.
Right.
Professor Wu used this great analogy in his lecture about a bird flying versus a pedestrian walking around a building.
Okay, I'm intrigued.
But
Tell me more about this bird and pedestrian.
okay, imagine you're trying to get from point A to point B in a city. If you're a bird, you can just fly straight there.
Right.
In that case, the Euclidean norm, also known as the L2 norm, would be the most appropriate way to measure the distance.
Okay.
But if you're a pedestrian, you're stuck walking along the streets, right?
Right.
You're limited by the grid-like structure of the city, so you might have to walk further to get to your destination.
Right.
And that's where the L1 norm or Manhattan norm comes in.
Okay.
It measures distance like a taxi would have to drive,
Uh-huh.
taking into account those right angles and turns.
So L1 for taxes, L2 for birds. Got it.
Yeah.
But Professor Wu also mentioned something called the L infinity norm.
Yes.
What's that all about?
Think of the L infinity norm as choosing the longest possible path.
Okay.
Let's say you have several options for getting from point A to point B.
Uh-huh.
The L infinity norm is like saying, I'm going to choose the route that covers the most ground.
So it's not about finding the shortest distance, but the longest.
You got it.
Okay.
You're essentially looking at all the components of the vector and picking the one with the largest absolute value.
So it seems like we're building up a set of tools here.
Yeah.
And each norm is like a different kind of measuring stick for distance.
That's a great way to put it. Now, the really cool part is that all these norms we've discussed, L1, L2, L infinity, they're actually special cases of a more general formula called the LP norm.
Wait, a master formula. That's pretty neat.
It is.
Okay.
By tweaking the value of P in this formula, you can generate all those different types of norms.
Oh, wow.
For example, if you plug in 1 for P, you get the L1 norm.
Okay.
If you plug in 2, you get the L2 norm. And if you let P approach infinity, you get the L infinity norm.
Okay. I'm starting to see how this all fits together.
Cool.
But what about this L0 norm thing?
Yeah.
Professor Wu mentioned it, but he also said it's not technically a norm.
Right.
What's the deal with that?
It's a bit of an oddball, but still a helpful concept. The L0 norm basically counts the non-zero elements in a vector. We call this the cardinality. It's like asking, how much real information does this vector hold?
All right. I think I have a handle on the different types of norms now,
Right.
but how do we actually calculate them? Can you give me some examples?
Absolutely. Let's use the vector 3, 4 as an example.
Okay.
Professor Wu used this one in his lecture, so it'll be familiar.
Okay.
We'll start with the L1 norm.
Okay. So for the L1 norm, we need to think about that taxi driver navigating a city grid.
Right. It's all about adding up the absolute values of each component of the vector.
Right.
In this case, it would be the absolute value of 3 plus the absolute value of 4.
Which equals 7.
Yes.
So the L1 norm of 3, 4 is 7.
Exactly.
What about the L2 norm, the bird's eye view?
For the L2 norm, we use the Pythagorean theorem.
Okay.
Think of our vector as the hypotenuse of a right triangle with the components of the vector representing the lengths of the other two sides.
Okay.
So we square each component, add them together, and then take the square root.
So it would be the square root of 3 squared plus 4 squared, which equals 5.
Exact.
Got it. The L2 norm is 5.
Yes.
Now what about that L infinity norm?
That one's the simplest to calculate. We just pick the component of the vector with the largest absolute value, which is 4 in this case.
So for the vector 3, 4, the L1 norm is 7.
Yep.
The L2 norm is 5, and the
This
L
is-
infinity norm is 4.
That's right.
That's pretty cool. They all represent different ways of thinking about the size of that same vector.
Exactly. And each norm gives us a different perspective, just like the bird and the taxi driver have different ways of navigating the city.
I'm starting to see how these norms could be really useful tools for understanding data in different contexts.
Yeah,
But I bet they get even more interesting when we apply them to real-world problems.
you bet. And that's what we'll explore in the next part of this deep dive.
Awesome. Looking forward to it.
It's amazing how a seemingly simple concept like length can become so nuanced and powerful when we start thinking about it in terms of norms.
Right. And I'm really curious to see how these norms play out in like real-world scenarios.
Yeah.
Professor Wu hinted at some applications in his lecture,
Yeah,
but I'd love to dig deeper.
absolutely. One area where norms shine is machine learning.
Okay.
Imagine you're trying to build an algorithm to predict, say, housing prices
Okay.
based on a bunch of features, things like square footage, number of bedrooms, location, and so on.
Okay, so each house would be represented as a vector with all those different features.
Exactly. Now, in machine learning, we often use norms to measure how far apart different data points are from each other in this multidimensional feature space.
Okay.
And this is where choosing the right norm can make a big difference.
So why are certain norms better suited for certain machine learning tasks?
Yeah.
It seems like they all measure distance in some way.
They do, but the way they measure distance can impact how the algorithm learns.
Okay.
For instance, the L1 norm is often used for feature selection.
Feature selection, remind me what that is again.
It's basically the process of figuring out which features are the most important for making accurate predictions. Think of it like this. You're trying to predict housing prices, but maybe the color of the front door doesn't really matter.
Right.
The L1 norm can help us identify and discard those less relevant features.
Interesting. So how does the L1 norm do that?
The L1 norm focuses on the absolute differences between the components of the vectors.
Okay.
This makes it less sensitive to outliers, those data points that are way off from the rest.
Right.
And in some machine learning algorithms, being less sensitive to outliers can lead to a more robust and reliable model.
So is that why the L2 norm isn't always the best choice?
Yeah.
Seems like the most intuitive way to measure distance.
The L2 norm is super common in many fields.
Right.
From physics to engineering to finance.
Yeah.
It's the one that corresponds to our usual notion of straight line distance,
Uh-huh.
but it can be more sensitive to outliers.
I see. So depending on the type of data and the problem you're trying to solve, you might choose a different norm to get better results.
Precisely. And this is where the concept of norms really starts to shine.
Yeah.
It gives data scientists and machine learning engineers a way to tailor their approach based on the specific characteristics of the data they're working with.
Okay, that makes a lot of sense. What about the L infinity norm? Does that come up in machine learning too?
The L infinity norm is maybe a bit less common in machine learning,
Okay.
but it still has its uses. Remember, it's all about finding the largest component of a vector.
Right. The longest path idea.
Exactly. Now, imagine you're designing a system with certain constraints.
Okay.
Maybe you're building a bridge and you need to make sure that the stress on any single component doesn't exceed a certain threshold.
Uh-huh.
The L infinity norm can be really helpful in these situations.
Because it helps you focus on the most extreme values.
Exactly. It's like saying, I need to make sure that no single part of the system is overloaded. So even though it might not be as widely used as the L1 or L2 norms, the L infinity norm has its own unique applications.
This is really making me see norms in a whole new light.
Yeah.
They're not just abstract mathematical concepts. They're tools that can help us solve real-world problems in all sorts of domains.
And then choose the approach that makes the most sense.
This deep dive into norms is really highlighting the interconnectedness of math and the real world.
Yeah.
It's not just about abstract theories. It's about using those theories to gain insights and solve real-world problems. And to our listeners, thank you for joining us on this deep dive. We hope you found it as enlightening as we did. Until next time, keep exploring, keep questioning, and keep learning.